The length of a phasor, like a vector, represents its magnitude, its maximum value, its amplitude, in a certain sense. The projection, the shadow of that vector on the x-axis, the horizontal axis, we are told by this slide, indicates the actual current as a function of time. This feels like I'm struck by how similar this feels. Back in 231, when we talked about sorry, I gotta untangle my sheet here. Back in 231, when we talked about oscillation, we said that the motion back and forth of a mass on a spring is describable as a projection of circular motion. You know what? I'll just pull up the diagram. I'm going to try to pull up the diagram. And it made me think, at the time, it still does, of Plato's allegory of the cave. We are, well, in Plato's allegory, there are prisoners chained to, I don't know, the floor, the wall, something. Chained, constrained so that they can only see a particular wall. And what they see on the wall is their entire understanding of the world. And they see this thing move back and forth. And they say, okay, that's a thing moving back and forth. But what they don't know, you know, they are piled here on the ground in front of the screen, I suppose. What they don't know is that behind them, elevated behind them, they can't see this. There is, in fact, a setup like this, a turntable with a ball and a source of light behind. And it's only the shadow that they see. That the world we experience is only a shadow of what is really true. that every observation we make is only sort of participant in the essence of a greater thing, some some platonic form of that thing, and we're only sort of experiencing a piece of it. I'm sitting in a chair right now, and I know that it is a chair, but I don't. It is not every chair, right? Yeah, I have sat in chairs that are different, and I still know it's a chair. Like I still recognize this and that and the one downstairs as a chair, which, as far as Plato is concerned, means that they are all participant in some greater idea of chairness, which isn't particularly real. Um, it just it seems to be so because I can recognize them all as forms of chairs. So there must be some sort of true chairness, and the more chairness a thing has, the more I can recognize it as a chair. Could I sit on a table? I suppose. Is it kind of a chair? Maybe, but it doesn't have as much chairness as it has tableness. You know, what the hell is he talking about? It's a fair question. I think about this metaphor like augmented reality glasses. The turntable isn't actually there. It's only a thing that we see once we put on the AR goggles of enlightened analysis. It's a means through which we can interpret and make sense of the results in front of us. We see a thing moving back and forth. And at the time in 231, we had reached a point where we had a differential equation, not unlike the one that we solved a couple days ago. And at the time in 231, we hadn't taken diffie-q or even calc 2 necessarily. So like the integral techniques that go with separable differential equations, we might not have even seen them. And so it takes something of a leap of faith to say, suppose I have put on these AR goggles and what looks to you like motion back and forth is actually describable as the shadow only of motion in a circle. And we can track, we can relate them. If we happen to imagine, if the AR goggles are set so that the right rotational rate, the right omega, and the right amplitude, that the turntable and the rate at which it's turning are correct, we can, suppose there's like a little knob on it, one for the amplitude, one for the angular frequency, right? And if we get those set just right, we can get perfect alignment between the back and forth motion in the real world and what we're seeing in the goggles as the shadow of circular motion, which means we can use circular motion and everything we know about circular motion, sines and cosines, and the unit circle and all of that. We can bring that to bear to further solve the situation. We ended up saying the other day that the three-way response of an RLC circuit depends on the relative values of the resistor, inductor, and capacitor. We talked about the value of a discriminant in a quadratic characteristic equation, and we said that based on its sign, there are three distinct responses, three distinct sort of families of response: underdamped, critically damped, overdamped. And the underdamped response was the one for which we introduced complex notation. We started with Euler's identity. We proceeded from there to derive relationships for cosine theta and sine theta. I just want to remind us, because this was a week ago now, right? It wasn't only Tuesday. Time is out of joint. And we added the two equations, and we ended up saying, just for clarity, that and to remind us, also because I'm still a little bit annoyed with the with that minus sign that caused so much trouble that day. Sorry for the jumpy deal here. We said that today I want to return to Euler's identity. Have you proved it? You know where it comes from?
Euler's identity? Yeah.
Where?
Well, e to the x is defined as 1 plus x, or wait, no, it's, yeah, 1 plus x squared over 2 factorial, and then it goes on in that manner.
Okay.
And cosine is, all the odd exponents combined, well, with like the plus and minus changes. That's what the I comes in. That's really useful. It changes to a negative for the odd. Or maybe it's the opposite. Something like that.
Something like that. Yep. So you're talking about power series.
Yeah, that's right.
Okay. That's the thing you're talking about?
Yep.
Cool. Why is that true?
Um, it had to do with like Newton's method or something. I don't, there's a way to do it. This is like Calc 2. I don't remember.
Sure. No, there's absolutely a way to do it. I just wanted to remind us that this was a thing we'd seen before, and that we do, in fact, we did at one point prove that this is true, and we proved that that you're right. Cosine of x has a series representation that I think just has plus signs in it. I'm a little bit unsure. I feel like it has minus signs in it because doesn't sine have minus signs in it?
Give me a second. I'll pull up my notes.
How would we prove it? And
It
just
does have minus signs.
yeah, where do the minus signs come from? I'm a little bit because e to the x doesn't have them, right?
Yeah, the minus signs come from the I, and you know how I has the cycle every fourth root. It'll cycle back. Not
Okay.
root, exponent. So you write square root of -1 equals I, and then square it, you get -1, and then cube it, you get negative I, and then to the fourth you get just
All right.
1 or something.
Okay. So based on this relationship that we wrote, we could reproduce that thing. If cosine theta is expressible in terms of e to the x.
I found it. Cosine of well, I did it for pi, but cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth, and then it'll be minus again, so on and so forth.
And sine uses the other terms.
Yeah, and then you could take the I out.
Right.
It's really pretty. Like the was it Euler's equation? Where it's like e to the pi I equals -1. It's gorgeous.
I know. I completely agree with you. I totally agree. Um, I want to plug a textbook for just a second. Because I know some of us are looking at different resources. I know some of us are following along with Young and Freeman. I know some of us have the 6 Ideas text. I know some of us are using OpenStax. There's another book that is really good. Where is it? Here it is. If you haven't, checked out this book, Mathematical Methods in the Physical Sciences by Mary Boas, do. It's fantastic. It's a really good book. My physical copy of it must be at the office somewhere. I didn't bring it home. I should have, but I guess I have.
What's the name again?
Say again?
What was the name again? It was mathematical something or other.
Mathematical Methods in the Physical Sciences. I use this book. Well, this book was assigned to me in undergrad, and I keep coming back to it. Undergrad was a long time ago. Really nice. Really nice text. And the reason I like it, one of the reasons I like it, chapter 1, I have no idea why it's formatted this way, but chapter 1, let's do this. No. Chapter 1, it starts with series, and everything builds from there. I think it's a really neat way to present what we sometimes talk of like the higher math, right? The next step is complex numbers, and then partial differentiation, and then vectors and Fourier series, like, and it goes through and builds on the foundation established by infinite series, which I think is just a great. It is really nice. It's a really nice way to present things.
It's interesting that it mentions partial differential equations and then ordinary after later on.
Partial differentiation is defined before ODEs. Yep. And that's what I'm saying. It's a really interesting text. And some of the front matter talks about, why the book is organized the way it is, and so on and so forth. And you could just, some of it is not intended necessarily to be sequential. It might just be referential. In other words, you look up what you're looking for and move on. But it's a really interesting text. And like I said, I keep coming back to it. What's cool about it is that when we're talking about Euler's formula, we can start from the series, which we have proved using Taylor's strategy, right? It's a Maclaurin series. We could do the same thing for e to the x. Definition 8.1, which I'm guessing, yeah, is again the series, which we find just with successive differentiation. This is the great thing about generating these power series is that there's no necessarily like no complicated integrals or anything, like there's no weird techniques. It's just taking derivatives like over and over and over again and setting things equal. It's algebraic almost, especially because we're just talking about the power rule. It's a really powerful, I think, way to kind of start things off once we're building these things. But once we have the power series for e to the stuff, cosine of stuff, and sine of stuff, then writing Euler's formula is a matter of matching patterns. Yeah, it's a matter of doing a slight reorganization and including the imaginary number I. But it's definitional. And we can prove it. We can prove Euler's identity, or Euler's formula, or whatever you want to call it. And then this is the next part. We have justified writing any complex number as an amplitude r, a magnitude, because the magnitude of e to the I theta is 1. Magnitude.
So we're gonna be.
Go ahead.
Sorry. So we're gonna be dealing a lot with polar coordinates. It looks like.
Not really. I just want to use this idea that we can represent any quantity, any complex quantity, by which I mean to include the voltage responses that we got from our differential equation. That we can write any complex quantity in this form as e to the I theta times some magnitude. I just wanted to kind of, I've never been very comfortable just using a thing, like here's Euler's formula, ta-da, and let's use it. I dislike doing that. It always bothered me. I was like, well, where the hell did that come from? That's cool. Where did we get that from? Is that just a thing? Is it true? Like, is that just part of math? Like it's baked in, 2 + 2 is 4, and that thing is true? And well, kind of, yeah. But how do we show that? That's why when the Young and Friedman text just presents the result for a damped, for an LRC circuit, and just says, here's the formula, like here's the function, and you're like, what? But why? Wait, how did you get it? Anyway. Um, all right. So with a little bit of digging back into our memory banks, we've agreed that any complex number is expressible this way. To make it line up with our analysis the other day, I'd like to change I to J so that I don't get confused when I talk about a current I. E to the J theta. It's the same thing. J is the square root of -1. Same relationship, just a little bit of a different notation. What is the idea? What is going on? If I take the complex number z and multiply by e to the j phi, where phi is some other angle, not theta, what is that idea? What happens? What's the result? Z, replace it with what we know, e to the j theta times e to the j phi. But this is the product of two power expressions that share a base. And we know what happens. We add the exponents. So this is r e to the j theta plus j phi. And we could factor out the j. Multiplying by the exponential expression e to the j phi has the effect of changing the angular orientation of the complex number z. We took what it was, on the complex plane, x plus jy somewhere here, and then this is has a magnitude r, found in the usual way, Pythagorean theorem. And this is theta. Multiplying by e to the j phi has the effect of, we keep the same magnitude, r, so we take the same vector, and now we have oriented it at a different angular spot, which is the sum of the two angles. Take a thing whose initial value, well, not value, but if I'm going to, all right, wait a minute, hold on, one thought at a time. E to the j phi. The radian argument here, phi, could be expressed as a function of time. That as time goes on, the argument phi increases, and the what apparently happens is that complex number z rotates around in the complex plane. When phi is 2 pi, we're back in the same orientation we started from. When it's 4 pi, we're back. When it's, I don't know, pi, we are anti-parallel our original direction, our original orientation. And I'm explicitly thinking here about the e to the j omega t that showed up in our solution to the differential equation. E to the j omega t has the effect, if we're multiplying some coefficient, has the effect of taking that coefficient and rotating it around at a particular rate in the complex plane. Suppose let's do it this way. Suppose those three things were true. And then we took the whole shebang and multiplied by e to the j omega t. Each time we multiplied, it would have the effect of taking the original complex number v sub l sub 0 and rotating it in a time-dependent way in the complex plane. What we originally started with indicated this way. Shoot. I was really hopeful that I could rotate this. I can't. All I can do is resize it. Ah, that's frustrating. Suppose t has a particular value. We end up rotating all three, preserving the relative orientation between them, rotating them all, the whole arrangement, by the angle in the complex plane that is associated with the value of omega t. Think again about the allegory of the cave, about the AR goggles. The turntable with its ball making the shadow, it's not actually there. It's an augmented reality. It's an enlightened reality device to better describe reality. Are the voltages complex? Are they sometimes entirely imaginary? And if so, how would I know the difference in the real world? There's no substance to the imaginary component of this whole story. It is visible only in the AR goggles. The fact that we're rotating in the complex plane is a enlightenment device to aid our analysis of what's really going on. One-dimensional oscillation in time. Each potential difference across each circuit element has a maximum and a minimum. For real, I could take a voltmeter and connect it across that element and measure real values. I could actually do that. I don't have to imagine it. It's a thing I could do for real. So what am I measuring? If I am imagining this sort of rotating vector arrow thing, what I could really do, I'm measuring the real component. How's that script R work? There, that'll work. We take the real part. Now, what do we end up with? I want to make sure the phase relationships are what they should be. That what we actually measure are sines and cosines, or cosines in phase or out of phase, I guess. How should we parse this? Let's use a different color. From the Euler identity that we've now proven, or at least that we've seen a proof of. And what is the value of e to the j pi over 2?
Isn't it just J?
Yeah. Does that make sense to everybody? Got a thumbs up? Other thumbs up from folks? Another one or two, and I'll believe you. Cool. All right. Just for my own sanity, because it's been a long day. Again, we could use Euler's formula. Yeah, okay. So if we distribute the j we end up with that because j times j is -1. And if we take the real part,
Is that where the 90-degree shift comes from?
the fact that it's sine,
No. Multiplying by j gives it a 90-degree shift, doesn't it?
yeah.
Love that. That's cool.
Enforces the fact, because cosine omega t plus j sine omega t, that's the just time goes on. We take the real part of e to the j omega t, we just get cosine. And there again, cosine and sine are 90 degrees out of phase. And this sort of initial setup, this initial definition, of the initial value of the potential across the inductor in terms of an imaginary sort of rotating turntable in the complex plane allows us to preserve the relationship between the inductor voltage and the resistor voltage at all times. At all times, these two things will be orthogonal, will be 90 degrees out of phase. And by the same sort of token,
Would the subscript be C or
yes, I've continued to do that. I'm consistent with that. I keep making that mistake. Yes. All right. What does this have to do with the potential difference across the source? Now, based on this analysis, we can just write down the current, the function that represents the current from Ohm's law. Exactly as we supposed. that the current that describes the AC source is a cosine function, given these initial conditions. The time-dependent voltage across the source is expressible as the time-dependent resistor, inductor, and capacitor voltages, which means we can plug in what we know. Now, the potential difference across the source should also be real. Like I should be able to measure it with a meter. So here I'm thinking maybe there's some maybe there's the real part of something here. But I know that the time-dependent resistor is the real part of VROE to the j omega t. And then the inductor is the real part of VCVLO e to the j omega t. And the capacitor VC0 e to the j omega t. All right. So we can just take these real parts that we found a minute ago. What is this the real part of? It's an interesting question. I expect, well, no, I don't expect. I insist that the time dependence of the source have the same form as the time dependence for everything else, because we're driving the system at frequency omega. I want to know what the initial complex value is for the source voltage. I want to know what the phase angle is, essentially. No, okay. Why am I bothering with cosine? Why am I bothering with the trig functions? Why can't we just start from here and divide the whole stupid thing by e to the j omega t? Let's just get that out of there. It's in every term. The real part, in other words, of e to the j omega t is whatever it is. It's the same. So we take the real part of that, and we're still left with taking the real part of v sub s sub 0 and the real parts of v sub r sub 0, v sub l sub 0, and v sub c sub 0. Real part of e to the j omega t is just cosine omega t. There's a cosine in every term. Throw it out. Before we, so like, if this is true, then that's true.
Mm-hmm.
Okay. So then what happens?
Then if we look at the three vectors again, we can add them up, and then we get a triangle that describes the source, similar to the one that we were looking at before.
Try from the like animation.
Yeah.
Triangle.
So it'd be the.
All right. Is to treat these like factors. And then to factor out an e to the j pi over 2 from the other two terms.
Would that e still be there?
Yes.
Hmm.
Is that a problem?
Oh no, I was just wondering. I was wondering if it would just be e to the -1, because we took out a j pi over 2.
Oh, see, I was thinking multiplication. So I was thinking e to the j pi over 2 times e to the j negative pi.
Hmm.
If we're thinking, if you're thinking about e to the j pi over 2 raised to the negative 1, like that,
Mm-hmm.
we can't factor out.
I see. Yeah.
E to the negative,
Wouldn't that just be -1?
negative, negative 1. I think you're right.
And then that would be j.
Just j, right?
Mm-hmm. Which is what we said earlier. So we get a really nice simplification here. And that part is looking like R. Or I guess Z, but
Yeah, because we said
or
this was supposed
almost.
to be b sub s sub 0 was going to be
Hey, I got a quick question. So that
Yeah.
e to the negative j pi, why'd you turn it into a -1?
be, well, should we have kept it?
Well, no, it's definitely better to simplify it, right? I was just a little confused on
Oh, then you just
logic.
plug it into Euler's identity.
Ah, I see. Okay. All right, that makes more sense than what I was thinking.
It's trying really hard to be an alpha. Is there such a triangle?
A triangle that holds true for all three of these things? Or
Well, so I'm thinking I want to end up with that. So I
mm-hmm.
can write it as e to the j alpha.
Mm-hmm. I mean, wouldn't it just be a triangle with a hypotenuse of 1?
Why 1?
Because either the cosine or the sine, it's over 1. So the ratio between cosine and the hypotenuse, or the cosine, the one of the legs, and the hypotenuse would be that.
I don't think it can be 1. So in other words, you're saying that this is VR and this is VL minus VC,
Mm-hmm.
but the Pythagorean theorem pretty much guarantees the hypotenuse isn't 1, right?
Oh yeah. So it would just be the square root of VR squared plus L minus, or VL minus VC. And then that way we can have the e to the j alpha.
As long as we include a magnitude,
Mm-hmm.
right? In order for this to be the cosine and this to be the sine, there has to be some non-zero magnitude, right?
Mm-hmm.
That thing.
And that was the triangle that I was trying to, I guess, allude to, but I just didn't know how to get to there mathematically.
Does that work? It works. This is great because now we can say and this angle alpha explains the difference between the phase of the current, which is the same as the phase of the inductor, same as the phase of the resistor. Wow. Come on. And the phase of the source. And if we think about a similar triangle, I want to get the colors right. Inductor, red, blue, green, inductor, resistor, capacitor. Red, blue, green. Let me draw it this way. Small inductor. If we tried to add these leg vectors, red and green would add to something slightly smaller than red and green. This way, right? And if we added the sum of those two with the resistor, those things are perpendicular. We need the Pythagorean theorem. What is the phase angle between the sum of the three and the resistor itself? Alpha.
And I don't know if I'm jumping ahead here, but you can see a nice, I guess, representation of resonant frequency, because earlier we saw that when the red and the green are equal to each other, that was resonant frequency, which just means that it's the maximum projection of the source.
If red and green are equal,
Yeah. Or at least in the animation that you showed earlier.
if red and green are equal, then their sum is 0. And that means that the power supplied and the power delivered are completely in phase and maximally delivered, I suppose. In the non-resonant case, the magenta vector is by definition larger than the blue vector. Has to be, because it's the hypotenuse. Which means that since the same current passes through everything, we're not delivering as much power as we could with this particular circuit because it's miscalibrated. It isn't resonant. We are delivering power only according to the resistor, which is the cosine. Well, it's related to the cosine. Yeah. the current is the same everywhere. So if we multiply by the current, we're talking about the power supplied. Well, we're talking about the peak power supplied that could be supplied, I suppose, with this amplitude source and the actual power dissipated by the resistor. They are different by a factor of cosine of this phase angle between the voltage response across the resistor and the source. That's called the power factor. It's cosine of that phase angle. Now, something I still don't quite know yet. Let me go back to the animation. This is the situation we're talking about. I've got the colors are backwards, and I apologize for that. Here's my question. All we did was change the frequency. All we did was change, like, actually the frequency. It's labeled F instead of omega. We don't change the resistor, the capacitor, the inductor, or the source. But we still achieve resonance. We still achieve this situation where the potential difference across the inductor and capacitor are the same, where these two phasors have the same length. There is a frequency component to the length of these phasors. What is the story with that?